Hello everybody, this is Dr. Christopher White, and in today's presentation we are going to be focusing on Paleozoic life history. So in this presentation we're going to be focusing on invertebrates. So an invertebrate is of course an animal that does not have a backbone, and they're a very important group. They make up about 95% of all animals on planet Earth, so obviously their first appearance in the rock record and their subsequent evolution is of great interest to geologists. Okay, let's get going. So, life in the Paleozoic. So, by the end of the Precambrian, we had achieved a few important things. So, first of all, we had complex, multicellular life. So, if you remember, at the end of the Precambrian, we had a group of animals which we called the Idiocarian Fauna. We had also established a clear distinction between plants and animals. So, by the end of the Precambrian, we had these two distinct groups of life, essentially. And by the end of the Precambrian, we also had the first indications of skeletons. Now remember, skeletons can be internal or external. So if you remember, these indications of skeletons are essentially in the form of either fragments of what we think might be, parts of a shell, or they may be shell-like structures that were made of organic material. So something like chitin, which is what insect skeletons are made of. Now the problem is, of course, is that we're not 100% certain that they were actually, internal or external skeletons, so we have to be careful in our analysis of them. But it would seem that we probably had some shell or internal skeleton-like structures existing by the end of the Precambrian. So during the Paleozoic, what will we see? Well, we'll see the appearance of hard skeletons. Now that can be an exoskeleton, like an insect or a mollusk, or it can be an internal skeleton, like ours. We're going to see a significant diversification of life. We're going to see lots and lots of species evolving as we move our way through the Paleozoic. We're also going to see the establishment of the major classes of animals. So if you remember, by the end of the Cambrian, we only really had about 4 of the main animal phyla actually accounted for. There are several other groups of animals for which we don't have any fossil record at the end of the Precambrian, so we have to assume that they make their first appearance in the Paleozoic. And of course, we will also see the movement of plants and animals from the marine environment onto the continents. Okay, so we're going to begin with the small shelly fauna. So if you remember, the first traces of shells or mineralized coatings appeared in the Idiocarian fauna right at the end of the Precambrian. And now we know the Idiocarian fauna was successful because we find them at numerous locations on every continent with the exception of Antarctica. So the Idiocarian fauna are followed by the small shelly fauna. Now the picture behind the text here actually shows you some of these small shelly fauna fragments. So these are sub-millimeter to several millimeter long organisms or parts of organisms. So the small shelly fauna might not actually be a complete organism. It could be part of a larger shell, for instance, that's just been broken up. So the small shelly fauna are made of either silica, calcium phosphate, or calcium carbonate. Now the interesting thing is that in the modern environment you tend to get animals that use these materials to make their shells, but they tend to be in limited environments. So for instance, organisms that tend to use silica to produce their shells are very, very common in areas like the North Pacific, because the conditions in that area are advantageous for the use of silica to make shells. In contrast, over much of the rest of the world, calcium carbonate is the dominant form, and so organisms that use silica or calcium phosphate to make their shells tend to be less common. So the thing that we see with the small shelly fauna is that we have animals which are making their shells out of all of these 3 different materials in the same location at the same time. Now this is very, very important because it gives us a hint about the concentration of calcium and carbonate in seawater. So one of the things that we notice is as we move from the Precambrian into the Cambrian, we believe the amount of calcium carbonate dissolved in seawater achieved saturation. And so once your seawater is saturated with calcium carbonate, it doesn't take much effort for an organism to be able to take that calcium carbonate from the seawater and use it to make things like shells. So the fact that we're seeing a mixture of calcium carbonate, silica and calcium phosphate being used implies a couple of things. Either the concentration of calcium carbonate in the seawater hadn't achieved saturation yet, so it wasn't advantageous to use calcium carbonate to make your shell, or what we're looking at is life just going, right, what is the best material to make a shell with in this environment? And so, a bit of experimentation is going on, and in the end you will end up with the correct material for that particular location. Now, as far as we can tell, most of the fragments of the small shelly fauna are actually parts of larger mineralized coatings. So they aren't, an individual shell in their own right, they're a fragment of a shell. In terms of actually representing discrete organisms, only a few of them can we actually say, right, this probably comes just from one organism, this particular shell is complete. So if we just have a look at these images of small shelly fauna fragments, essentially you can see that most of these look quite fragmentary. I mean, for instance, if you look at number 7 here, it looks like a plate from a larger shell. They probably would have been overlapped one on top of another, a bit like a suit of armor, for instance. In contrast, number 1 here, well, number 1 does have the possibility of being a discrete organism in its own right. If you look, you have this kind of horn-shaped shell, and you can actually see here where the shell is split open, you can see the wall right there, and you can actually see the interior of the shell was probably actually open, so an organism could have been able to live inside there. So the small shelly fauna were followed by the appearance of large skeletalized animals. So these are the organisms we're more familiar with, things like trilobites, for instance. Now, developing an exoskeleton, so an external skeleton, so a shell, has several advantages from an evolutionary point of view. Number 1, it provides protection from ultraviolet rays. So you have to remember, by the end of the Precambrian, the amount of oxygen in the atmosphere wasn't, that high. It was still, building up. Now, the oxygen in the atmosphere is obviously used for breathing, but some of it gets turned into ozone, which obviously, becomes part of the ozone layer, which offers us protection from ultraviolet rays. The problem is that as we transition from the Precambrian to the Cambrian, the ozone layer would not have been, as robust as it is now. And so this would have meant that more ultraviolet radiation was making it to the surface of the Earth, and as I'm sure you know, organic life doesn't really like being exposed to large amounts of UV rays. It's bad for them. And so having a shell offers you a certain amount of protection from ultraviolet rays. It also helps prevent drying out in an intertidal environment. So all the organisms that we have at the end of the Precambrian were fully marine. If they went into any kind of environment where they would be exposed to the atmosphere for any period of time, they would have very quickly started to dry out and die. Now, having a shell, on the other hand, helps you to avoid this problem. So, number 1, having a shell just helps to, trap the moisture against your body. But also, if you are something like a mollusk, you can actually close your shell, and seal yourself off from the outside environment for an extended period of time. So, having a shell essentially helps you to create your own little protected environment in which you can survive during periods in which conditions aren't advantageous to you. So, for instance, if you live, in a beach environment, obviously half the day, conditions are going to be in your favour. The beach will be covered in water. You'll be able to feed, move around, reproduce, etc. But for the other half of the day, essentially, you just close up your shell and you just sit there and do nothing because the conditions aren't right for you. The presence of a shell also allows animals to increase in size because they provide attachment points for muscles. So let's think of organisms that do not have skeletons. So something like a sea cucumber, for instance. Well, there's a limit on how big animals like that can get. because at a certain point the animal is going to become so big and it's going to have so much mass that without a skeleton it's essentially going to flatten itself and turn into a giant pancake. So by having a skeleton, be it internal or external, it offers support to the body and it stops it collapsing. Now obviously as you begin to develop these very hard shells, obviously they make really good solid attachment points for muscles. This means that muscles can become larger as well, so your animals can start to use the shells to actually get bigger. So over time, shells are advantageous in that they obviously offer you support for your body, and over a longer period of time they will also offer the opportunity for the organism to increase in size. The final one is of course the most obvious. A shell will also provide protection from predators. And we actually have numerous examples in the fossil record where we can see, in the Cambrian for instance, the shells of animals that have definitely been attacked by a predator. We can see the tooth marks for instance, but we can also see that the organism has survived. We can see the damage is being partially repaired, which would imply the animal has survived the attack. So having a shell is obviously a very significant evolutionary advantage because it makes it more difficult for predators to eat you, and obviously if you can avoid that fate, that makes it more likely that you will reproduce successfully. So this brings us on to the Cambrian Explosion. So the early Cambrian is marked by a rapid increase in fauna, particularly those with skeletons. Now this is an accurate statement but also an inaccurate statement. So yes, in the rock record what we suddenly see as we go into the Cambrian is we see this explosion in life that has skeletons, mostly exoskeletons, so shells. The one thing is though is that there was probably a lot of life around at that time that did not have skeletons. The problem is, of course, is that soft-bodied organisms do not tend to fossilize. And so this means in the fossil record, well, what are we going to see? We're going to see loads and loads of animals that have hard shells because they fossilize, but we're not really going to see many examples of animals that had soft bodies because they don't fossilize very often. And so this statement is both correct and incorrect. Now, this explosion in fauna that we see in the rock record is referred to as the Cambrian Explosion. Now, the increase, so this sudden appearance of all these different organisms, was actually problematic for 19th century scientists who supported evolution. So evolution essentially said, right, the process of achieving animals like these that have these complex shells would obviously take lots of time. There'll need to be a large build-up period during which small incremental steps are taken until you achieve the life that you see that has shells. But the problem is, of course, is as we've discussed, if you look at the Precambrian rock record, there are no organisms that have shells, so there's no indication of this steady build-up, these steady small incremental changes that evolution would suggest should be taking place. So the lack of the macrofossils in the Precambrian and the sudden appearance of all of these organisms that had shells were a bit of a problem. It was like you had literally gone from inventing the wheel to a jet aircraft. You jumped, intermediate steps. You couldn't see what the evolution process was to get from one to the other. So obviously this was a bit of a problem, but it was solved by the Idiocarian fauna. So we know the Idiocarian fauna now essentially fills this intermediate space and essentially helps us to explain how we go from the Precambrian, where we have a group of soft-bodied organisms that don't have indications of having had shells, all of a sudden to a load of animals in the Precambrian that do have shells. Now, we should also remember that when we're using the term explosion, we are talking fast in a geological sense of the word. So the Cambrian explosion itself actually took place over about 20 million years. So, this wasn't an instantaneous thing. This is something that took a long time to occur. But from a geologic point of view, it was very, very fast. So the next question is, well, why do we see this explosion? What is it about the start of the Cambrian that really says to life, this is it, this is the moment where we go for it? Well, there are four main reasons. The first one is climatic. So the Cambrian environment was warmer than the previous Proterozoic era. So if you remember, during the Proterozoic we had several large glaciation events, particularly towards the middle and end of the Proterozoic. So this means global water temperatures would on the whole have been pretty chilly. And, life doesn't really like those conditions. Then all of a sudden you go into the Cambrian, the Earth as a whole starts to warm up, global water temperatures begin to increase, and obviously life is going to find that a bit more advantageous. We are also going to see changes in ocean chemistry. So as we've mentioned, as we transition from the end of the Precambrian into the Cambrian, we begin to see indications that the ocean is becoming saturated with respect to calcium carbonate. So the concentrations of calcium carbonate are important. Oh, by the way, I apologise, I appear to have missed a space right there between Ca for calcium and reached. The addition of extra calcium and extra carbonate, now the presence of the carbonate will increase ocean pH as well, will drive carbonate mineral precipitation, because if your seawater is either saturated or supersaturated with calcium carbonate, well then all life has to do is come up with some kind of process that allows it to take that calcium carbonate from the seawater and use it to make a shell. And it turns out that life is actually super effective at doing this. Using organic molecules, it's actually surprisingly easy to start stripping calcium carbonate out of seawater and using it to make mineralized coatings. And obviously the presence, this saturation or supersaturation of seawater that appears to occur at the Proterozoic Cambrian boundary appears to be one of these factors that really helps in shells becoming, something that's easy to achieve, and as such all of a sudden it becomes, from an energy point of view, quite an advantageous thing to have, because it takes less energy to make a shell now, and so having a shell obviously offers you a lot more protection, so it works in your favor. At the end of the Proterozoic going into the Cambrian, we also see more continental shelf environments. Remember, life loves a passive continental margin. It's safe, it's boring. And so at the end of the Proterozoic going into the Cambrian, we have the breakup of the supercontinent Pangaea. This is going to increase the amount of passive continental margins around, and this means essentially you have more areas where you have these nice, stable, shallow marine environments in which life can flourish. And of course the final factor, once again, predators. So a shell or a mineralized coating obviously offers you protection from predators, and one of the things that we see as we move into the Cambrian is we begin to see animals appearing that are definitely predators. They have all the indications of being an animal that will actively hunt another organism for food. And so obviously once you have predators establishing themselves in the food chain, well in that case you're going to start an arms race, and essentially having a shell is one of the best defensive options you can possibly have. So in all probability the Cambrian explosion was probably a combination of all of these factors acting together rather than just one of them. The question we want to ask ourselves is, although the conditions were correct for organisms to begin to develop shells, why did they actually do it? So, conditions can be absolutely perfect, but it doesn't necessarily mean an animal will develop a shell. So why do it? Well, the first thing we need to bear in mind is when we're talking about shells, at least in the very early Cambrian, we're really mostly talking about exoskeletons, so an external shell. So please bear that in mind. Okay, so what are the reasons why having a shell becomes advantageous to an organism? Well, the first way in which it's advantageous is it gives you a method of getting rid of excess calcium. So obviously if you live in a marine environment, you are going to be ingesting large quantities of seawater, and as we've already discussed, seawater at this point is saturated to supersaturated with calcium carbonate. And one of the methods by which that calcium carbonate can be encouraged to exit the seawater and crystallize is through the use of organic molecules. And unfortunately, if you're an animal, you're nothing but organic molecules. So this is a bit of a problem. You're made of a material which is naturally going to encourage calcium carbonate to exit seawater and begin to crystallize. And so you need to get around that problem, because it could, in theory, it could become quite serious. So imagine if you are, obviously ingesting large quantities of seawater. That means you have large quantities of seawater passing through your gut, and you start having calcium carbonate crystals nucleating on your gut lining. Well, obviously, eventually that means you are going to be unable to digest food, and you will starve. So what you really need to do is you really need to encourage the calcium carbonate to form somewhere where it's not going to hurt you. So instead of it, for instance, forming crystals inside your gut lining, you instead encourage it to nucleate on your surface and essentially give you a mineralized coating. So it's a relatively simple way of taking the excess calcium carbonate that you are going to ingest anyway and doing something with it. Another reason why having a skeleton becomes so helpful, especially exoskeletons, is that they are, from a biologic point of view, cheaper and easier to build than internal skeletons. So, if you look at the skeleton for an oyster, for instance, it consists of two halves. It's a very simple structure, but it's also extremely robust. If you've ever tried to open an oyster, you will know it's actually not an easy job. And these very simple exoskeletons are very easy to make, they're very energy efficient, and they offer a very high level of protection. Now compare that to our skeleton, the human skeleton. Well, it's very, very complex, it's much easier to damage, and from a purely, from a pure energy point of view, it takes a lot more effort to actually make. So having exoskeletons, at least to begin with, is, from a biologic point of view, advantageous over trying to form an internal skeleton. The final reason why having a shell, offers such good conditions for organisms in the early Cambrian is that the cold conditions in the Proterozoic meant that organisms had insufficient energy for biomineralization. So if you're living in a cold environment, typically you will obviously direct your energy into whatever keeps you alive. And in most cases, expending energy on making a shell just isn't something that you want to use your limited resources for. However, as we've discussed, once you get into the Cambrian, global water temperatures begin to increase, so seawater begins to get warmer. And so all of a sudden, you need to direct less of that energy to other processes that would have kept you alive in colder conditions. So now you have a bit of excess energy. And so what are you going to do with that excess energy? Well, you can use it to essentially give yourself a shell, which obviously offers you a lot of protection. Now, if we just go back to this point, if we look at modern environment, exoskeletons are rarer in modern polar marine organisms than in modern tropical marine organisms. So if you were to go to somewhere like the Great Barrier Reef, you would find that lots of the invertebrates in that environment will have shells, and those shells will be very big, thick shells. In contrast, if you were to go to a colder environment, let's just say off the coast of Antarctica, you would tend to find that most of the invertebrates would have, either very, very thin shells or no shells at all, purely because it's not advantageous to have one. You've got to direct your energy into things which are actually going to keep you alive. Now, it's clear that once shells begin to appear, marine organisms that have them have a significant evolutionary advantage in most cases, and so that's obviously going to direct evolution towards the development of shells in a really, really big way. So let's take a moment and think about the modern marine ecosystem. So by looking at modern marine organisms and the adaptations that they have developed in order to become successful in their preferred ecosystems, we can gain an insight into ancient species. So organisms are separated based on their preferred ecosystem. So organisms that live in the water column are termed pelagic, and they're split into two subdivisions. The first subdivision is plankton. So plankton are free-floating organisms, so essentially they just float around in the water, and they're further subdivided into two groups. We have the photoplankton, so those are the plankton that photosynthesize, essentially plants, they create their own food. So that's organisms like diatoms, dinoflagellates and algae. We then have another class who are called zooplankton, and those are the animals. So that's organisms like jellyfish, foraminifera and radiolarians, and they will actually actively hunt the phytoplankton in some cases, or they will simply grab small food particles out of the water column depending on their preferred method of food collection. So if your organism is not passive, so it doesn't just float around in the water column, it's going to be called it's going to be part of the nekton group. It's going to be nektonic, and these are the swimmers. And most swimmers are vertebrates, so organisms like fish, although there are invertebrate organisms as well, like the cephalopods, that's squid, octopi and cuttlefish. In terms of organisms that live on the seafloor, those are referred to as benthos. So in terms of the seafloor environment, we have three main subgroups. So we have the epifauna. So those are animals that live on the seafloor, so something like an oyster. We have epiflora. Those are plants that live on the seafloor, so think of something like kelp. It anchors itself to the seafloor to keep itself in one spot. And then we have infauna. Those are animals that live and move through the sediment. So that's organisms like worms, for instance. So we have these three main groups. We have the plankton. They live in the water column, but they are free floating. They just float around. They're passive. We have the nektonic organisms. Those are in the water column, but they are active organisms. They actively propel themselves. And then we have the organisms that live on the seafloor, which are the benthos. So benthos can also be split into two further groups. There are those organisms that stay in just one location. Those are called sessile benthos organisms or benthotic organisms, while those that move are termed mobile. So as well as considering where the organism lives and whether they move or don't move, we must also consider how they obtain their nutrients. So obviously there's five main subclasses of organism based on how they obtain their nutrients. Obviously the first group is going to be the photosynthesizers, so the plants. They're going to use sunlight and they're going to use that to make proteins. Then we have the suspension feeders. So those are organisms that actively filter small animals or particles of food from seawater. And so they'll typically have specially designed appendages, often covered with very, very fine feather-like attachments, and they will grab small particles as they essentially pass by the appendages, and then the food obviously gets passed down to the animal's stomach. Obviously there are the herbivores, organisms that eat plants. There are the carnivores, animals that eat meat. And then we have the sediment deposit feeders. So those are organisms that ingest sediment and they filter out any organic material they find in that sediment, use that as a food source, and the rest of the sediment they just pass through their body and excrete. So this diagram here is taken from the textbook, and it just gives you a breakdown of the general environments and a few examples of organisms which are which cover each of those subgroups. But don't worry, it gets more complicated. So an ecosystem contains several trophic levels. So a trophic level is a tier of food production and consumption within a feeding hierarchy. So it's actually easier than it sounds. So in the beginning there are the primary producers, which are referred to as autotrophs, and these are animals that make their own food. So that's the phytoplankton, the plants, organisms that will produce their own nutrients. Now these primary producers will then be eaten by the primary consumers. The primary consumers are typically herbivores or suspension feeders. The primary consumers are then eaten by secondary consumers, who are going to be carnivores. The secondary consumers will then be consumed by the tertiary consumers, who will also be carnivores, etc, etc, etc. And eventually, of course, you will end up with what we commonly refer to as the apex predator, which is the most dominant predatory organism in that particular environment. There are also another group of organisms we need to remember. There are the transformers and decomposers. So these are organisms that break down organic material into its constituent compounds. And so these compounds will then obviously re-enter the seawater, and then they will be used by the autotrophs to essentially metabolize, to produce new proteins. So we have to have the transformers and the decomposers as part of our chain, otherwise nutrients from unconsumed organic material would never re-enter the system, and we would have a bit of a problem. So this diagram here, once again taken from the textbook, it looks quite complicated, but it's all relatively straightforward, as you can see. So we're going to start off with sunlight, obviously, then we're going to have the organisms that can produce their own food, so something like the phytoplankton. They'll be consumed by the herbivores will be consumed by small predators will be consumed by large predators, and it all makes relative sense. In terms of organisms when they die, obviously a number of things can happen to them. They can obviously be decomposed, in which case the organic molecules will re-enter the water, and then they can be used by the photosynthesizing organisms to make more food. Obviously, we can also have any organism that dies, it can fall onto the seafloor, where it will be consumed by benthotic organisms. Its body might be broken up, in which case parts of it will be consumed by suspension feeders. And obviously then any organic material that goes into the sediment can then be consumed by sediment-eating organisms. And so essentially what you can see is we have this relatively simple cycle through which organic material is constantly being recycled. Okay, so this is a good place to stop part 1. So get up, have a walk around, get a glass of water, take 5 to 10 minutes to relax, and then please come back to part 2.